Tangerine SDR database and control system architecture from Bill Engelke at the University of Alabama. Bill's AB4EJ.
All right. Thanks, Nathaniel. This is Bill Engelke, AB4EJ with the University of Alabama, and we're going to talk about the Tangerine SDR database and control system architecture. The point is, I want to get across what will the personal space weather station network be. To build up to that, we have to talk a little bit how the system is architected and designed and how the Tangerine SDR will work within this network. And that's kind of in the reverse order I'm going to be talking about it. I'm going to say a few things about the Tangerine's design and how it is relevant to how you use it within a network. So our goals here for the network itself is to build a network of receivers that can observe the ionosphere by watching Doppler shift and WWV and other stable signals. There are plenty of other things you can do with this as working on phase one of a multi-phase project. So we got to walk before we run. At the same time, we want to give hams a way to closely monitor propagation at their own stations. The idea here is we would like hams to be interested in this system even apart from the scientific objectives. And so maybe folks would like to get some real good propagation information at their own site and at the same time help out the scientific community by providing data. This is the network of receivers is very similar. If you're familiar with SatNogs, that's a crowdsourced system for observing telemetry of things like CubeSats that are not monitored by any nation state. So the only way you get 24-hour-a-day information on what your CubeSat is doing is by using the SatNogs network. Our idea here is to do something quite similar to that for the personal space weather station network. So what will this network be? Well, we've got a group of universities and research facilities. You've already seen all their logos. What we hope to do is have several hundred and maybe thousands of inexpensive software-defined radios. And when I say inexpensive software-defined radios, I'm also including these Tangerine SDR in that, because you can buy software-defined radios that cost up to any arbitrary amount. But this basically the two major systems that we're designing, the Case Western Reserve system and the Tangerine. So the idea is we expect to have these in ham shacks, but also at institutions, schools, universities, any research institutes that are interested in supporting the work. So each one of these, the Tangerine SDR includes a single board computer. Now, it doesn't necessarily have to be a single board computer. We're architecting the software that runs on that system to run in Linux. So hopefully any box that runs Linux should be able to act as a control system within a Tangerine. Obviously, if you want to connect the low-speed Pi hat kind of things, it has to be something compatible with that. So the idea is we want to get data analysis for science objectives plus a personal propagation monitor for each user. Here's a top-level view. The station locations here are just examples. The emphasis is on North America, but users in other locations are also welcome. If we're going to focus in phase one on what's happening in WWV, we obviously have to focus more on North America than anywhere else. And again, this is a phase one thing. We foresee that this could be rolled out in other parts of the world, and everybody has their own set of stable signals that they could observe. Phase one, we'll put the database at the University of Alabama. That's also a cost decision. As I've joked, only semi-jokingly, we have quite a server farm here. Our friends in IT found out that Auburn University had a little bit bigger data system than we did, so we had to put in a bigger server farm so that our system can be just some few percentage larger than what they have at Auburn. And so they have some excess server capacity that they make available at very reasonable cost, and so we will be able to use that. And I'll talk a little bit more about how we're going to deal with that in a minute. So let's talk about of the personal space weather station network. On the left, you see the Tangerine SDR, which includes both the data engine that Scotty has talked about and the local host. That's what I call the single board computer. For example, Odroid N2. There's more than one way to design that. You could also use various levels of Raspberry Pi, although if you take a look at the kind of speeds that the data engine will be providing, especially when monitoring more than one channel at a time, you can quickly swamp some of the really cheap devices. So I've been doing all my testing with an Odroid N2, which is fairly powerful. There are other comparable ones. One or more local sensors, a magnetometer you see here, and this would be at your location. And it'd be connected through the internet to the space weather network. What we define as there will be a control system. I'll talk about how you use that in a few minutes, and a database. And we expect to make clones of this database at multiple sites. We'll initially build this up at University of Alabama with the idea that it can be replicated in other locations with a minimum of mirroring the database in at least one other location. So in case we have a problem with something at UA, the database will not just go dark on us. So what is in the Tangerine SDR? That's been talked about quite a bit, so I'm not going to spend a whole lot of time talking about it. But the idea is you have a couple of ports, antennas that you can monitor, and that's connected to this single board computer via Ethernet, gigabit Ethernet, using a GPSDO clock and a magnetometer. Again, there's more than one ways to connect these up. This is just for illustration purposes. And that is what your Tangerine is. That's what you'll have at your local station. As far as the software that runs on the single board computer, there is this dotted line here indicates the content of what's running on the single board computer. There's a couple of parts to it. There's something called main control. That's something written in C. It uses the asynchronous package libuv, in case you're familiar with that. It handles commands from a local web server. I'll talk about that in a minute. It also handles a high-speed data feed from the data engine. The data comes via UDP. We're not using TCP due to the overhead of it. The plan is that it will save data in the digital RF format. There's several different formats. I'll talk about that in a moment. Our idea is we want the thing to be able to decode FT8 and whisper signals and manage uploads to the central control system and also interface to GNU radio. There will be a browser-based system. The idea is we don't want you to necessarily have to be some kind of world-class expert to use this thing. We want it to be able to get set up and used via a web front end that's fairly user-friendly, so that in schools where you don't necessarily have a high-end IT staff, they'll be able to get this thing up and running and use it. So this web-based system is using Flask and Flask WT forms for any nerds and geeks in the audience. Just certainly. So as far as data collection, our idea, and this is aspirational, whether we actually end up achieving this is still to be determined. We want to be able to monitor up to 16 band segments at a time, and hopefully maybe more. We envision 4 different types of data collection. Let me talk through those. First, what I call a snapshotter. That is a once per second waterfall snapshot of the FFT, that is the spectral content of one of the channels that you take a look at that once per second. That is good if you have low internet bandwidth. We know that a lot of home users especially, they're very limited on how fast a data rate they can upload. So if you have that situation, the snapshotter is what you would probably use for data collection. Second item is what we call ring buffer. That is continuous local storage for 24 hours. That stores the data in digital RF format and uses the digital RF ring buffer function so that it deletes anything older than 24 hours when new data comes in. And then the capability to upload based on a request from central control to upload a time frame of that, like give me from this time of day to that time of the day, not necessarily the entire thing because that would take an awful long time to upload. Third type of data collection we envision is what I call fire hose. This is for places that have a local supercomputer or local server farm right on the same local area network with everything hooked up with gigabit. That is just the entire content of whatever channels you ask for, just spooled directly out to wherever. And that, by the way, I should mention, the central control database does not play a role in this. Finally, propagation monitoring. This is once per minute decode of, I shouldn't say JT8, FT8 and whisper on up to 8 bands. This is quite similar if you're familiar with the similar functionality on the Red Pitaya using the Pavel Demon software. It works very much like that in that once a minute it does a decode of whatever channels you have configured, and it gives you a list of what things it's heard and in terms of spots. So what stations have I heard? That allows you to determine their location, and from that you can determine propagation.
Okay, 4 minutes.
4 minutes?
Yeah, so we're going to try and get into questions.
Yeah, so handling of collected data, it goes through local storage on request and gets uploaded. Snapshotter, local storage, it goes through GNU radio, that's how we do the FFT, and then upload from there. Local propagation is decoded and local display and storage, and then upload spots to PSK Reporter and WhisperNet. That doesn't go to the central data system. And then finally, Firehose just goes to a local supercomputer. There's not very much more to talk about on this. The central control system is, that's going to be a CentOS-based system which has a web front end and database management. We're using Django, Celery, RabbitMQ, and MariaDB, again, for the real geeks in the crowd. How you'll use it. You'll build your you use a browser to connect to the central control system and sign up for an account. The account will allow you to get a security token from Central. You paste that into the Tangerine web interface. That will identify your Tangerine to Central. Again, we've stood on the shoulders of giants here. This is very similar to the way the SatNogs network works. Then you start collecting data. And you can also, at the same time, do local propagation analysis at the same time. Data analysis, Tangerine SDRs collecting data using Snapshotter or ring buffer. The central system will request data, which then gets uploaded. We save data in a database for analysis. Spectrum data will be stored in digital RF format. Science users will be able to run analyses and download. Anyone will be able to download data. It's going to be all open source and open data. And you'll be able to get local propagation reports by FT8 and Whisper. Why would anybody want to do this? You get a chance to be part of new science, compete for wallpaper like SatNogs. Everybody gets a kick out of seeing how high they can get their station up in the rankings of how much data has been uploaded. And you also get a chance to see an ongoing snapshot and ongoing trend information on what propagation looks like at your location. So let's take a look at the front end as it is so far. I will, well, submit questions via the chat window. I'm going to hop out of this and show you the front end. This is what I have so far. I have built a simulator for the data engine that I talk to through a gigabit Ethernet switch. It's all laid out on my workbench here, and running on the Odroid is a system like this. It gives you this front end. You go in, you tell it to make its connection. It'll crank for a minute, and then this is basically restarting the main control program and reestablishing communications with the data engine. It tells you we're up and running. Some of the configurations you're able to do, you can go in and set up various components, put your token in here, set up the data engine, pick up what frequencies you want to monitor the channel, turn the channels on and off, pick which antenna port, center frequency, and bandwidth each channel is going to have. Set up throttling of upload data. And this is something that's a particular favorite of mine, where you can put in a bunch of call signs that you want to monitor. And when these call signs happen to occur where your system picks them up, they have occurred in Whisper or FT8, you can get a notification. And then you can get an email. And if you happen to have one of those email services that can send text messages, the idea here is when a certain station you're watching for is heard at your station, you get a text message about it. So you can kind of watch for that DX station to occur at your station to be heard, and don't necessarily have to sit at the radio. So as soon as you get that text message, you rush to the radio and try and work them. So that's one of the fun things that we envision. You could also set this up to monitor D-Star, but that's probably not as interesting for most people. And so I think I've raced through that. One final thing, I've got this running here. This is using simulated data. It's data collected some time ago, but it's decoding FT8 spots. And here it shows the number of spots at each frequency band we're monitoring. I would probably do this graphically. I just got this working the other day, just output it by text. So we see we got in the last minute 50 spots on 7 megahertz, 34 spots on 10, 71 on 20, etc. So you can observe which bands are open and how much they have been in the last minute. I anticipate we can also, look at the last 15 minutes, the last hour, various things like that, kind of analytics. So because we are short on time, I'm not going to go into a whole lot more detail on that. But all right, so this kind of covers the objectives that I had. And Nathaniel, you wanted me to leave some time open for questions.
Yeah, I think we're actually out of time, so we are over time, so I'll have to go right to the next presentation. Again, people, please put your questions in the Google Doc, and then the presenters, please answer the questions.